Okay. So Eshma and Alicia, how you guys doing?
Good.
Good. All right. Then what I wanted to do today was look at the actual questions that I wanted to look at yesterday, because somehow I had a feeling that maybe you hadn't done it to your fullest ability. Um, and since sharing the screen doesn't always work with all the question formats, um, why don't you each log into the My Classroom and bring up the Unit 6 questions. Okay. Um, so how about, do you want to do like just little breakout rooms? I can do a breakout room for all my Zoomers and well, I guess a breakout room, or just put the people who are, well, you're all Zoomers, I guess. The people who are actually together on campus in another room, just do that. And I'm just gonna pick, there's a couple specific ones that I wanted to look at, made a kind of list of the ones that I liked. And so the first one, gotta refresh my memory. I just have a list of numbers. That's all I have. Number 8. So I'll go to number 8. And I'm gonna drop my how many do I have? I'm gonna do 2 breakout rooms for the no, I want to do this. 2 breakout rooms for the people who are we're gonna put everybody in breakout rooms. I'll let you guys talk about it and then I'll call you back. Okay. Questions? That's right. Number 8. Go ahead. All right. Ava and Alicia, what'd you guys come up with for this one?
We thought it was A or D, but I think we both were leaning at D at like in the last seconds.
Okay. What drew you to A?
Huh?
What drew you to A?
The single circular and then the multiple circular chromosomes.
Okay. And what drew you to D?
Because I just know for a fact that the eukaryotic DNA has multiple linear chromosomes. I'm
Yeah.
not quite sure about the prokaryotic one though.
Oh. Okay, so that's good. So we've worked with the chromosomes a lot, and we've seen that X shape whenever we were doing like our mitosis and meiosis. So we know that they're not circles, right? So they are linear.
Mm-hmm.
So that can rule out A. And hopefully, I mean, I mean, certainly humans have way more than one chromosome. I'm not sure if there's anything that only has one chromosome. I don't know. Certainly most things don't. So that pretty much rules out B. So you're left to linear chromosomes, and then it comes down to what do the prokaryotes look like if they're linear or they're circular. And so bacteria are definitely well known for having the circular chromosomes. You may remember the slide. It was brief, but in the replication slide, it showed them duplicating their circular chromosome. We've talked about that in a couple other places. So yeah, D was the correct answer. Good job. Was that enough time? Yeah. How about, can we do this instead? Can we and this one I'll put you in your breakout rooms, and when you're satisfied that you have an answer, just go ahead and come back to the main session. And then if we're taking too long, I might just close the rooms on you. So let's look at number 10 next. So this should be doable after our activity that we did the other day in class. So we're gonna number 10. All right. How about my group in the Founders Lounge? What are you guys thinking it was?
D.
Okay. Why D? What told you that?
Process of elimination.
Okay. Why did you eliminate the other ones?
Well, this is so we noticed that C and D are opposite answers. So
Okay.
we assumed that it's probably one of them because that's how tests usually work. They give you two similar answers but different. And then we just counted them and realized that A has more short fragments. And so, yeah,
So how did you know it has more short fragments?
because I counted 1, 2, 3. That has 12. That has 9.
This doesn't work.
Can I leave now? Oh,
So what do we know about how the movement of the bands and the size of the bands are related?
Eliza said A.
Well, isn't it like shorter? It's like longer, kind of.
If
Like
it's shorter, what's longer?
the length, like how far it goes. Sorry.
Yep. So shorter fragments migrate farther. So based on that, along with the Founders Lounge's good use of test taking skills, which one has more short fragments?
B.
B has more short fragments, right?
So you're right. We just had the wrong reasoning.
Yeah.
Sick. I'll take it.
Yeah, and A and B answers, you can't really, that doesn't really mean anything. You can't infer that from just one little region and who has more, right? Because like you could look at speed, like we did humans, right? And all the humans had different bands, right? We're all equally complex, right? We're not either others ancestors, but it's just what we know about the way the DNA is mutated. So
is it C or D?
it was C.
Okay.
Species B has more short fragments than species A. Okay. So close. Good reasoning. All right. Let's look at number 11. Oh, we did this one in class already. Never mind. Number 12. This is a fun one. This is mostly about interpreting the graph. And so I wanted to kind of just do this because this is just a good skill that you will often have to do on the test. So, I mean, it does relate to the material, but more of it is just turning like what you see in words and turning that into graphs. So I'll do the same thing. I'll let you guys pop into breakout rooms and work on it and come back to the main session when feel like you're done.
We were on C or D.
Okay. Let's look at those two and figure out what the difference is. Okay. What attracted you to C?
We were looking for a graph where there was growth in the beginning and then like a change somewhere after the inhibitor was added.
Okay.
And then also like an opposite reaction after it was removed.
Okay.
So we crossed out A.
Yep. I mean, based on this, the inhibitor is doing nothing, so that seems right. How are B and D different? I mean, I know what's different about the lines, but what does that mean is happening?
Oh, for B and D.
So this is
they're
actually
both increasing.
Yeah, so it's saying that the number of proteins are actually decreasing,
Mm-hmm.
then coming back, versus this one they're staying the same. And then if you remove an inhibitor, would you expect the numbers to decrease?
No.
No, you'd expect them to go back, right? So before you had inhibitors going up, then when you remove the inhibitor, it goes back up again. So D would have been the correct one.
Oh yeah, it's not B because like it would just stop growing, right? Not just decrease.
Right, exactly. Yep. We wouldn't expect them to automatically start decreasing. You have to put something in there that would also digest the proteins. Okay, good job. I'm gonna skip a few. Number 15. This one looks like fun. So looking at the lac or trip operon in this case. And let's mix up the breakout rooms a little bit.
Put us with Ava.
Hmm?
No, Ava's gonna be like, no thanks.
I was unmuted.
I know.
Okay.
Okay. All right, so we're at number 15 we're on, okay? Okay. So this one was probably a little bit more difficult, I'm guessing. Basically, you have the operon here. It describes how it works. Talks about it's an example that trip operon is a repressible operon, so it's normally is on, but then something works to turn it off, right? So its default state is on. And so in this case, you've got your TRPR gene, so like the trip repressor gene transcribes to make the RNA, makes your repressor protein. And if there's no tryptophan around, you see it cannot bind with the operator. But if it does have tryptophan around, it turns into this shape, so it can go here and then stops the RNA polymerase, so that shuts down the transcription of the gene and turns it off. All right, Founders Lounge, did you guys have an idea as to which one it might be?
Don't say it.
C. We said C.
You said C?
Yeah.
What made you say C?
We think it's C because it's an educated guess. Yeah, process of elimination.
You said for the last one.
That didn't work out for you last time either.
Well, maybe this either.
He's ruthless.
All right, how do you know, Founders Lounge, how do you know it's not A?
It's not A because doesn't work because the normal expression of TRP doesn't cause the TRP operon to be transcribed because it affects. Can you not? It affects whether or not it's transcribed. So, and that's saying it doesn't. So
Yeah, that's the exact opposite of what happens, right?
yeah.
So you know it's not A. All
Oh.
right, what about B?
It's not B because
It is B.
Oh, no, we said it was C. It's not B because it is still transcribed even when it's mutated because there's the active TRP repressor. It's the inactive TRP repressor that does it.
So yes, you're correct that it is going to, even if it's mutated, it's still going to be transcribed. So that part's correct. So that logic would work for you. There's also something else that's wrong with this. Oh wait, no.
Pair to share.
No, that's okay. Actually, I misread it. So this says if the operator sequence is mutated, the TRP operon is not transcribed. So that's basically saying if this is broken, this would not be transcribed. But we know that this is an off switch. So if it was mutated, you wouldn't be able to turn off the thing.
Yeah, that's what we said. It's B.
Okay. Then what's wrong with D?
I mean, D
said
is
C.
wrong because when TRP is mutated, it isn't transcribed regardless of tryptophan levels because it depends on whether or not the tryptophan is there.
Well, if this is mutated though, it doesn't matter if there's tryptophan there. So if TRPR is mutated, then none of this can happen. So you don't have your repressor. So if you don't have your repressor, what does that do to tryptophan production?
So it is D.
It is D.
We were close.
You were close. 2 off. So right, does that make sense? So if the regulatory gene is mutated, you can't make the repressor. If you can't make the repressor, the trip operon is going to be described no matter what. I agree. C is a tough answer to ignore. I think that of all the wrong ones, like I feel like that's okay-ish. So the TPR gene R codes for a repressor protein that has a DNA binding domain. But it's not so talk about this right here being the binding domain. It doesn't bind with DNA, it binds with the tryptophan molecule.
Oh, okay.
But I think I like that you guys did a good job at ruling out A and B.
Thank you.
You're welcome. All right. Number 16. Okay. This one should be easier, I think.
You weren't on the screen, so we couldn't see what number. And I don't think you said it out loud. You might have just
I
said,
don't know.
okay,
I might not have.
one.
I'll cut you some slack on that one. Did you guys have enough time to finish Ava and Sonara? Were you with Sonara this time? I forget who you're with already. So what did you guys think, Ava?
I didn't really know, but I suggested maybe A or C.
What did you like about A?
Well, I mean, it makes sense to me because the substrate fits with A. But
Yep.
yeah.
And it's only making C, right? So that makes sense. So that is right. That's the right answer.
Okay.
What's wrong with B? Anybody?
That's not true.
Right, because they're making totally different enzymes, right? This is kind of one of those ones where you look at it and it's like it almost seems too easy because you had that nice picture that makes it look easier, I think. The cell will remain healthy because enzyme C will undergo alternative splicing again, and so it's transformed into enzyme A. Is that possible? Can we turn 1, 2, 3, 5 into 1, 2, 3, 4, 5? No, right? We can't splice this and reclaim section 4, right? We could like turn, yeah, you can't re-add something back in, so that wouldn't work. And then will cell remain healthy because enzyme interactions are non-specific. We know that's not true, right? Enzyme reactions are very specific. Okay.
Is that a wrap?
No, not a wrap yet. Although, what's my battery at? How about we'll do, I've got 26%. We'll do one more.
Okay, sounds good.
You like that, Marin? So number 21.
We'll answer this one.
You want this one?
We gotta go.
All right, what do you think, Marin?
D.
Which one?
D as in dog.
D as in dog? I disagree. Why do I disagree?
I don't know, probably because I'm answering it.
Ashmaran, why do I disagree with D?
With D?
Yep. Anybody. Doesn't have to be Ashmaran. What's wrong with D?
Marin chose it.
That was not the right. No, that's not why. Do you think I got it out for you now, Marin?
No.
Okay. What's wrong? There's something wrong with D. Obviously.
Wrong step?
No.
Because DNA polymers doesn't synthesize the segments, right?
No, it does.
Oh, I really don't know.
So when you're looking at a replication fork like this, remember it starts replicating and it goes out in both directions simultaneously. And so you actually have, it has its own DNA polymerase molecule, another one. So it's not like one has to detach. These two and 4 are happening simultaneously. And 1 and 2, they're all happening simultaneously. So they all have their own DNA polymerase molecule. So what about A? You guys like A or don't like A? Anybody? It says 1 and 4 are synthesized continually. So it's a straight line. Do you guys notice how this one's a continuous line? This one's fragments?
Oh, well, I just looked at it.
And then, or we have B is 1 and 2 are synthesized in segments from 3' to 5'. So which way does DNA get written?
5' to 3'.
Yep. Read up, write down. So we write down from 5 to 3, 1 and 4 continuous. So that's the right answer.
Oh.
3 and 5 or 2 and 3 are segments, but they're going 3' to 5'. That's not correct. And then 1 is synthesized continuous from 5' to 3', which is correct. And 3 is in segments, synthesized in segments from 5' to 3'. Wait, that's right. 5 to 3, 5 to 3, 1 and 4 are synthesized 5, write down 5 prime to 3 prime. 1 and 3. Why is C not right? What is wrong with C? 1 is synthesized continually in the 5 prime to 3 prime. Okay, that is the right one. So what did I miss about A? 1 and 4 are synthesized continuously in the 5 prime to 3 prime direction. One and 4. I don't see any difference in those answers. Do you guys?
Mm.
1 and 4, right? Continuous, 5 prime to 3 prime, 5 prime to 3 prime. And then C, 1 is continuous in the 5 prime to 3 prime, which we just said, and 3 is synthesized in segments from the 5 prime to 3 prime. I feel like A is right as well. I feel like A and C are both right.
It does look right.
That's weird. Or if there's just a typo or something. The important thing I wanted you to get from there is the 5 prime to 3 prime, and then recognizing that some of them happen in segments, right?
Mm-hmm.
Because when you're going, yeah, 5 prime to 3 prime. Because it can't just go 5 prime to 3 prime without doing the segments. Because it's opening up here. So it's got to synthesize as it opens up, versus this one it can just build and add as it opens up. Okay, that's 3 o'clock. Tomorrow, my plan is that I'll be back and we can do our DNA gel electrophoresis lab. Who's not going to be in class tomorrow in the actual building?
Wait, do we have class tomorrow?
Oh, wait, tomorrow's Friday. We don't have class tomorrow. Never mind. I don't know. We'll obviously do that next week, because I was planning on doing this stuff next week anyway. So no time lost. So let's work on the lab. We'll work on that next week. No class tomorrow. I forgot we shifted days. And your homework is to finish this this guy, the multiple choice progress check for Monday. I think that's it, right?
Yeah.
Okay, okay. Okay. See you later. Bye.
Bye.